In molecular solids, the particles are held to each other by intermolecular forces. Molecular solids are soft with low melting points. Anytime I hear the word molecular solid, the first thing that pops into my head is butter. Butter contains only nonmetallic elements. It's soft. It has a very low melting point. That's a good anchor substance for whenever you are thinking about a molecular solid. Let's take a look at these three substances. They are molecular substances, that is, they contain only nonmetals. And the substance on the left, benzene, C6H6, is a nonpolar substance. And for that reason, the only intermolecular forces that we have between one benzene molecule and another are London dispersion forces. Phenol has hydrogen bonding as its strongest intermolecular force. Of course, all substances have London dispersion forces, but phenol exhibits hydrogen bonding because of the hydrogen here attached to the oxygen, and in effect that hydrogen bond is an attraction between this hydrogen and the oxygen on an adjacent phenol molecule. In the middle we have toluene, which is also entirely nonpolar. Anything that consists only of carbon and hydrogen is categorized as a nonpolar substance. So toluene is nonpolar, like benzene is, but its London dispersion forces are a little bit stronger than benzene's, typically, because it has more electrons. It has a larger molar mass, therefore it has a larger number of electrons, so you can get stronger instantaneous dipoles with toluene. If we look at the boiling points for these three substances, they follow a predictable pattern. Benzene has the weakest intermolecular forces, London dispersion only, so a boiling point of 80 doesn't surprise us. Phenol has hydrogen bonding, which is the strongest, so it has the highest boiling point, and toluene has stronger London dispersion forces than benzene, but not as strong as the hydrogen bonds in phenol, so that seems to make entirely good sense. Now what about the melting points? Benzene has a melting point of 5, phenol has a melting point of 43. If we follow this trend, we would expect the melting point of toluene to be somewhere in between 5 and 43, and we see that it is not. It melts at a much lower, much colder temperature than we would expect. And here's why. When we're melting it, these toluene molecules are in the solid phase. When they're in the solid phase, look at this toluene molecule. You have essentially benzene type ring here, which is a planar ring. And then down here you have what's called a methyl group, and it's like you have a tripod there. Kind of like, if you look on the left side of the screen, a music stand. See, the stand is the benzene-like ring, and then at the bottom you've got the carbon atom with 3 hydrogens, zip, 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 coming off. And think about it. If you were to stack music stands into a trunk, how many of them could you get in? Well, you couldn't get in all that many because that base tends to push the music stands farther apart from each other. Think about if you just had the top part of the music stand with the support column. How many of those could you put in a trunk? Wow, a lot. And they would be very close together. But as soon as you add this base on here with the tripod structure, then the music stands aren't nearly as close to each other, and you can't get nearly as many in the trunk. And we know that when particles are close together, the intermolecular forces are stronger, and when they're on average a little bit farther apart, the intermolecular forces are weaker. This is why toluene doesn't fit the trend of melting point, because in the solid phase they don't pack nearly as closely as either benzene molecules or phenol molecules. In covalent network solids, particles are held together in large networks by covalent bonds. So on the right side of the screen you see a bunch of atoms. They are held to each other in a giant network of covalent bonds. Now, this is different from what we have in a molecular solid, as we'll discuss here in just a minute. A few examples of covalent network solids. Something like diamond is a covalent network solid. To a certain extent, graphite can be considered a covalent network solid. Things with silicon tend to be covalent network solids. These substances are much harder and they have much higher melting points than molecular solids. With regard to the melting points, to get a molecular solid to melt, all you have to do is break or weaken the intermolecular forces between one molecule and the next. To melt a molecular solid, you actually have to put enough energy in to break all of these covalent bonds, and that takes a lot of energy. To review, in a molecular solid, the particles are held to each other by intermolecular forces. So here we see the difference between a covalent network solid and a molecular solid. You can see at the bottom of the screen, molecular solids consist of discrete molecules. A covalent network solid at the top of the screen consists of this never-ending lattice, this three-dimensional array, each atom of which is held to a number of neighbors, 3, 4 neighbors, by strong covalent bonds. In a molecular solid, the molecules are connected to each other by weaker intermolecular forces, which I've represented here by dotted lines. Graphite has layers of covalently bonded carbon atoms with delocalized pi electrons, similar to benzene having pi electrons. Therefore, graphite is a good conductor along its layers. The structure of graphite is a series of hexagons of carbon atoms that are covalently bonded to each other. And then in the next layer, there's another series of hexagons right above it. And in between those layers, we have delocalized pi electrons. Usually, these pi electrons are just moving randomly. But if you put an electric potential difference across these electrons, what they do is they all tend to move as a herd. And for that reason, graphite, although it consists only of nonmetallic elements, is a good electrical conductor along its layers. And these layers are held to each other by weak London dispersion forces. Unlike the bonds at each vertex, we've got a carbon atom, and the lines shown here are covalent bonds. Let's review molecular and covalent network solids. 1. In molecular solids, the particles are held to each other by relatively weak intermolecular forces. These substances contain only nonmetallic elements, and often the only intermolecular forces are London dispersion forces. Carbon with anything else solids are usually molecular solids. 2. In covalent network solids, the particles are bonded to each other by strong covalent bonds. Carbon only and silicon with anything else materials tend to be covalent network solids.